So chapter 17 was about equilibria, and our next two chapters are actually still about equilibria. In chapter 18, we deal with acid-base equilibria, and then in chapter 19, we move on to other kinds of equilibria, which include buffers, and then we resolve the lie that we told you in Gen Chem 1 that some salts were insoluble, which in reality, they're really moderately soluble, or just minimally soluble. So just kind of looking at the 5 things that are important then from chapter 18 before we kind of start going through our sample problems. The first is kind of qualitative aspects of acid-base equilibria, which are identifying, classifying, and reacting acids and bases. So we'll have 4 sample problems that we'll work through that kind of deal with that. Sample problems 1, 4, 5, and 6. Then we move into some quantitative aspects of acid-base chemistry and kind of a series of related equations that allow us to think about quantitating how acidic or basic a solution is. And then we deal with equilibria problems. And so there's the same 2 types of problems that we saw in chapter 17, which are really ones where we're given equilibrium parameters and we have to solve for K, and the more typical kind of problem where we know an equilibrium constant for a given acid or base, and we're going to solve for equilibrium quantity. So most problems are going to be of that type. So again, weak acid and weak base types of equilibria, so we can see the associated equations here. There should be an equilibrium arrow there. The associated equilibrium constants, and how difficult a problem is basically related to what we dealt with in chapter 17 and how directly that information is given to you. So about 5 sample problems that we'll work through dealing with equilibria with acids and bases, and a whole host of homework problems. And then in our last class, we moved on to talk about acid-base equilibria of salt solutions. And the idea is that when you have a salt that creates cations and anions in solution, those cations and or anions might behave as weak acids or bases and can contribute to changes in pH. So we thought about this both qualitatively and quantitatively, and we had a series of steps, and we'll go through, again, 3 sample problems to kind of deal with that. Thinking about who's in solution, evaluating their acid-base potential, and then determining if there's multiple components to acid-base potential, who's going to win out. And so we did this both qualitatively, asking the questions, are solutions acidic, basic, or neutral? And then a couple of problems we actually dealt with quantitatively, where we actually had to use ice tables and equilibrium constants to figure out what the actual pH was. And at the very end of the chapter, we kind of dealt with other aspects of acid-base chemistry. So understanding why we have the rules for acid-base chemistry that we talked about qualitatively on this first page, and that we'll deal with in some of these sample problems. So we kind of look at chemical structure to understand that. And then we look at Lewis acids and bases, so a much more inclusive definition of acids and bases that allow us to encompass a lot of the different species that might have acid or base potential that don't fall under Arrhenius or Bronsted-Lowry definitions. Okay, so our first sample problem that we're going to work through here, now that we just kind of reviewed an overview here, our first sample problem, 18.1 here, has to do with just classifying acid-base strength. So I'm just going to kind of highlight a sheet that was given out the day in class that we worked on this, and there were 2 slides that we had that I printed out for you so that you didn't have to worry about taking notes on them. And they're basically the rules for classifying strong acids and weak acids, strong bases and weak bases. So this is not information that will be given to you. This is kind of similar to how these species from chapter 4 were actually classified in terms of strong acids, weak acids, strong bases, weak bases. But we'll use this sheet as we work through the sample problem. So again, not a sheet that's going to be available for you, but it's one that I encourage you to use as you work through problems here, so that when it comes time to do these problems on an exam or a quiz, you're competent at it. Okay, so again, classify each of the following compounds as strong acids, weak acids, strong bases, or weak bases. So as we look at the first solution, it's a solution that contains potassium hydroxide. And this relates to some of the salt stuff that we'll deal with later in some sample problems. But if we had some potassium hydroxide and we put it into solution, what we're going to get, because all potassium salts are soluble, is we're going to get potassium ions and hydroxide ions. And as we learned from our Arrhenius definition, anything that directly contributes OH to solution means that that solution is going to be a base. And since this is a very soluble salt, it's going to make a lot of hydroxide. So this means that this is a strong base. And one of the rules that we have here when we're talking about strong bases, they're going to be water-soluble compounds containing oxide or hydroxide ions. And generally they're going to have cations of active metals. So pretty much almost everything in group 1A or the calcium, strontium, or barium, the heavier metals, that heavier in terms of weight in terms of group 2A. So we can see that this species is going to be a strong base. If we look at the second species here, we can see CH3CH-COOH. So I'm going to kind of draw out what this looks like. This, again, is an organic compound. So if we had to draw a Lewis structure, this is what this would look like. And one of the things you want to be able to recognize is when you see this COOH, that is a carboxylic acid functional group. And carboxylic acid functional groups are always going to be weak acids. And again, if we look at our sheet that we have here, carboxylic acids, general formula RCOOH, where this H is the ionizable proton, these are going to be weak acids. So another skill that's important that we have here is being able to look at the fact that even though there's a lot of hydrogens in this molecule, only this hydrogen is the ionizable proton. So if I were to ask you to make the conjugate base, for example, of this species, you'd take this hydrogen off and you'd add a negative charge here. These hydrogen atoms that are here are not ionizable. So ionizable protons tend to be hydrogens that are bonded to heteroatoms, such as oxygen or nitrogen. Okay, all carboxylic acids, weak acids. Our next one, H2SeO4. Not something that we've really seen about. So we have to remember one of the rules that we have here when dealing with oxoacids. So oxoacids, again, are going to be species that have ionizable protons, and there's going to be oxygen attached to another atom here. And so what we need to look at there is the number of oxygen atoms as compared to the number of ionizable protons. And if it's 2 or greater, that means it's going to be a strong acid. And again, if it's a weak acid, it's going to have only about a differential of 1 ionizable proton to oxygen atoms. And so here we can see that there's 2 ionizable protons, and we see that there's 4 oxygen atoms. So that differential is 2. There's 2 greater oxygen atoms than hydrogen atoms, so that means that this is going to be a strong acid. And not surprisingly, with this kind of sample problem, we've seen a strong base that follows our rules for strong bases. We've seen a weak acid that follows one of the rules for our weak acids. Again, we can see some other examples of weak acids. Hydrohyalic acids are generally strong acids except for HF, which is weak. So hydrohyalic acids, so hydrogens with a halide. The oxoacids, where again we have a smaller differential between the number of oxygens and the number of hydrogen atoms. Acids where hydrogen is not bonded to oxygen or a halogen. So again, we can see here these are not going to be strong acids. And then carboxylic acids. So the one that we haven't really dealt with yet because we had strong bases are weak bases. And one of the things that we'll see again, and this is why it was important when we were talking about functional groups, recognizing that any amine, so again, this is going to be a nitrogen attached to hydrogens and carbon atoms, and primary, secondary, tertiary amines are going to have different numbers of carbon and nitrogen atoms. But when we look at this, we can see that the amine functional group is going to function as a weak base. So if we were to draw out what the structure of this looks like, we can see that we have this group, which is an amine. And amine functional groups are weak bases. And keep in mind, don't just assume because you see a nitrogen that means there's an amine. This is a classic molecule that I like to put on exams that students get tripped up on. They see nitrogen, they immediately think, oh, that's an amine, that must be a weak base. But this is actually nitric acid. This is one of the oxoacids, and a very strong oxoacid because there's 3 oxygens and only 1 hydrogen. So in this case, we have a very strong acid that people see the nitrogen and they automatically assume that it's a weak base. Again, this is a very strong acid. So don't just see nitrogen and assume that you have an amine. Remember, it's nitrogen attached to some combination of hydrogen and carbon atoms. So qualitatively being able to classify acid and base strength is an important preliminary skill, because you're going to start seeing problems where I might ask you to predict whether a solution would be acidic, basic, or neutral, and you need to know the species that you're starting with.